Alright. I think... We good? Sweet. Okay. Alright. So... Today, I will be, doing my... Oh shit, hang on, I'm still not completely ready. Oh god damn it. Oh no. I've just forgotten some stuff that I had to do beforehand. Oh. Also, sorry about the laggy camera. I can't do anything about that. How's my voice? Like, I know probably no one's watching right now, but am I able to be heard properly? And let me just... Okay, let me just... Alright, now I won't really be able to view chat or anything all that much. Hang on. Alright. How's everything going? Sorry, I was sending a message there, but am I being able to, like, am I being heard properly? Lovely. Is also sorry about the laggy camera. There's not really much I can do about that. You know, just the webcam is really old and driver support is completely gone. So unfortunately, we're just gonna have to suck up with, I think this is, it says it's 30 FPS, but I highly doubt that. Am I being heard properly? Hang on, let me just, it says it's 30 FPS, but yeah, okay, so that seems alright, sorry about that. My microphone's a bit further away now because the cable can't reach as far. I redid my entire setup not too long ago. And so yeah. So I still haven't actually gotten everything completely set up. There's still stuff I need to do that I forgot to do before starting the stream. I just got a bit excited and I was also like, oh, I'm running a bit behind here, so just bear with me while I do that. Let me just pop out my chat real quick so I'll be able to like see it while I do things. Spider-Man on the wall, yep. He's still there, right around there, yep, there he is. So... Oh shit, this thing is still... Okay. I don't know where I can put my chat without it. Hang on, sorry guys. I love graphical issues with my system. It's great. Okay, I'll just do that, and then do that. I think that'll work. Yeah, right. So I've just gotten that done. This may be a bit of a slow start to the stream. Oh, god damn it. I haven't even signed into my goddamn GitHub, man. No, not sign up. sign in. So I had some technical difficulties earlier. I had to reinstall a new operating system on my PC. I've got an Ubuntu. Now, I was going to go with the newest Ubuntu 26.04. However, I couldn't because, what was it? Yeah, it was having issues with installing, and I had the same issues when I was installing, what was it, Ubuntu 24.04 on this thing. I managed to get that one working, though, a while back. You know, I managed to get, 24.04 working on this a while back. I had to disconnect from the internet while it was installing, otherwise it would just bug out and not do the thing properly. So I tried the same technique with 26.04, which seemed to work for the install, and then when I got into the system and tried connecting the network, it would detect the network, but I couldn't actually connect or do anything. My mouse is moving on its own. What the fuck? Yeah, okay, well that won't be too much of a big issue. I won't be using my mouse all too much. You know, yeah, so anyway, long story short, I ended up going with Ubuntu 24.04, what was it, Unity, with the Unity display manager. And they were having some slight graphical issues. I seem to have minimized some of them. But yeah, there's just some issues. I was going to go with a different distribution, however, the thing is I'm very used to Ubuntu. And so it's like, why change something when I don't need to? So with this stream, I'm going to be going over what I've done so far, because I've been working on this for around 6 months now. And, jeez, nice. I've been doing this for around 6 months now, and I'm finally at a point where I feel like I can start going over it with, on, like, live, basically, yeah, and, like, show it off more and get it out there, I guess you can say. Not that I really want attention or something like that, it's just, this is a hobby project and I'm incredibly proud of what I've done so far. So I just want to show it off and show how I do my programming stuff. And yeah, I just need to finish actually getting fully set up, because I'm yet to do that, which is really not that good. So yeah, I will, hang on, let me, right now, what I will do is, so you guys can check this out if you want, I'll put this in the chat. It is a link to the GitHub. Yeah, it has been a while since I've shown this to really anyone. Okay. So it's been a while since I've shown this to anyone. But yeah, so there's a link to the GitHub. You'll be able to see changes basically in real time. Well, not really, like, I still need to push them to GitHub and stuff like that. And before anyone asks, yes, I know I spelt millennium wrong. Okay, no, I'm sorry guys, but I spelt millennium wrong. It's meant to have 2 N's, not 1. I need to get a new GPG key up ready. Hang on, give me a second, let me just go. Pluma. This is a little text editor thing. I'm just going to put my, it's not GPG key, is it? It is GPG key, yeah. I need, because you can no longer use your password. Yeah, personal tokens, is it classic tokens? No, it's fine-grained. Wait, hang on a minute. No fine-grained token, classic tokens. Oh, yeah. I need to get another token, because you can no longer, when you push to GitHub, you can no longer use your GitHub password for it. You need to get a token, and tokens are really long. And I'm really hoping I don't accidentally show the key, because that would be incredibly bad. Generic new token classic. What's this token for? We'll just call this token something along the lines of... There we go. Expiration date. Let's give this one 30 days expiration date. I feel like that's a good idea, just in case if it does get leaked, I can delete it quickly, or if I forget to delete it or I don't delete it, then it'll be expired automatically. Okay, let me Google this actually. Window Manager, mouse on its own. Erratic mouse movement, touchpad sensitivity, disable touchpad. I don't have a touchpad. Okay, hang on. This is actually absurd, because I've had Ubuntu Unity on here before. Yes, so many Miku. Disable Wayland. I don't want to go back to X11, because, yeah, check for ghost input devices. There aren't any. This is a brand new. Okay, I need to get fucking GNOME tweaks now? God damn it. Hang on. So, Stormy, yeah, unfortunately it is AI generated, which is unfortunate. I didn't realize when I first got it. However, you know, they were a gift, so I kind of feel bad if I do take them down. I am thinking about replacing them, however I don't have any money, so I can't. Install GNOME. Oh, no, hang on. I don't want to display 244 possibilities. Hang on, shit. Not underscore tweaks, it's dash tweaks. Which... Oh. God damn it, my camera's died. This may happen from time to time. When my camera will just die. Yeah, there we go. That would be nice of you. Let's go. Tweaks. Go in a keyboard. Mouse and touchpad. Acceleration profile. I can't change the acceleration profile. Hang on a fucking minute. Let me go into the normal system settings and go mouse and touchpad. God damn it, man. Okay. You know what? I'm just gonna be... The stream didn't freeze, it was just my webcam. I'm just gonna deal with glitchy mouse, right? Anyway, let's go. Yep, just enable everything. Give me a second, this is taking longer than it should. Yeah. Okay, now I can't scroll. Now I can. Okay, I don't... code space. I don't need Copilot. I don't know why that's an option. I guess I can manage my Copilot with this thing. However, I don't have access to Copilot because I'm not paying, and I'm not going to be paying for that shit. Copy. Paste. There we go. got that now. Alright, so now I have the GBG key. I need to okay. Sorry about the whole delay in everything. I really should have, you know, done better at this. Let me just get the dependencies. That I need for this. I guess I can now show you guys this screen. Now the thing is, this is a vertical monitor, so I may sometimes need to manually readjust it. And as you can see right there, I'm not moving my mouse at all. I'm just holding my click button. That's how. Like, look. Hang on. Oh, yeah, like. It's crazy. Anyway. So those are the dependencies. If you go into the GitHub, as you can see, Zora ISO, mtools, grub PC bin, and grub common. You know, you need grub for the bootloader. Zora ISO, that's to make the ISO file, and mtools is a good way to just check hard drive stuff on like the virtual hard drive. It's a vertical monitor. That's what I mean. That's what I mean. It's really good for like programming and stuff because I can get more like vertical space. Yes, it really does. So now what I do is I'll go, let me just go ls, alright. So now I'll just go git clone https //github.com /GordOS. Yeah. .git. Cloning into GordOS, retrieving objects. There we go. Now if we go ls, we now have a folder called GordOS, and we just cd into that. And now here is where I need to set up the cross compiler, and yeah. So this part is not a pain, but it's not fun. So right now what this is the cross compiler. This is the guide for the cross compiler, GCC cross compiler from the OS Dev Wiki. This is the cross compiler that I use for the system, because, well, you need to compile your source code, and, well, I can't compile it without a cross compiler, otherwise I'll be compiling it for my specific hardware. However, there is no, technically, for this operating system, there's no specific hardware. The only specific hardware there is x86, which is 32-bit system. And so that's what I need to do. So I cannot use, so what I do is sudo apt install build -essential bison flex. This is just from the OS Dev Wiki, so libgmp3 -dev libmpc-dev texinfo and lib isl. Why do you hate Pinkie Pie, dude? Pinkie Pie's fucking incredible. -dev. And so there we go. give that some time. You can't see it anymore. God damn it, man. I fucking... Give me a second. I mean... Why, thank you. It is a good keyboard. Oh no, I'm fine. I'm just trying to see if I can get the terminal to Okay. Alright, well, I guess we're dealing with just manually scrolling the terminal window. So, now I need to get bin utils from the FTP GNU mirror. Bin utils with gold. I really should have done this before streaming, honestly. Like this. Oh, god damn it. So GCC 1610 tar.gz. Now GCC always takes a while to compile. don't. This mouse thing is really pissing me off. I'm just gonna unplug my mouse and plug it back in and see if that does anything. Okay, which one is my mouse actually? I'll figure it out. Got it. I think so. No, didn't fix it, for fuck's sake. Okay. Okay, so now... So now I need to do this. There we go. And so now we make bin utils, so we go cd dot. Mkdir to make a directory. Mkdir. Wait, hang on. ls home. Yeah, okay, so no, okay. cd, so mkdir src ls. Okay, and so now sudo md downloads bin utils to now sudo mv, oh shit, mv downloads gcc to src. Now cd into src and go ls, and there they are. Now go cd dot dot. Okay. Okay, hang on. Wait, hang on. Shit, I think I did this wrong. cd home / src ls. There, okay, never mind. I haven't done it wrong. And yeah. Huh. It's just glitching out for me, but not you guys, I think. How I understand all this, I mean, I'm just reading the not documentation, the fucking, what is it? What's it called? Oh no, it is glitching out for you as well. Nice. There we go. The OS Dev Wiki to do all this. So, oh, and I also know some of my commands, the commands myself. Like, yeah. So mkdir build dash bin utils. Yeah. Not bin utils. Utils. And so now we go cd build bin utils dot dot slash hang on ls fucking stop it cd build bin utils Okay. Alright, anyway, for some reason, is it... Oh, I know exactly why. I haven't untarred it. XVF, bin utils. There we go, now cd, build, bin utils. How do I stop this thing from... whatever, we're just gonna have to suck it up, guys. I'm sorry. Bin utils, configure, target equals $target dash dash prefix. Yeah, true. Equals $prefix. Now this one's in brackets dash dash with dash sys root dash dash disable dash nls dash dash. Well, I don't know when it's going to be flashy, that's the thing, like, disable where. Okay. Make dash J8. Oh, okay, for a second I thought my mouse stopped doing the thing, but no, it's still doing it. Now this can take some time to compile. Oh, that's true. The whole stream. Let me just go ahead. Edit. Or not. Okay, it's not letting me edit. Okay, there we go. Epilepsy warning. There we go. I'll put that in the bottom of the description. Now we go make install. Okay, now cd dot ls rm-rf. Don't need that anymore. Now we go gcc, so tar-xvf gcc. Alright, now gcc, this one takes a long time to compile, unfortunately, so now we go mkdir build dash gcc cd build dash gcc, and now /gcc configure target it equals $target dash dash prefix equals in brackets, not brackets, parentheses, not quotation marks. What is it? Yeah, $prefix. Now we're not into the good stuff yet. We're literally just doing some fucking a little bit. Anyway, prefix dash dash disable dash nls dash 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 enable languages equals C, C++, dash without headers, dash disable hosted. Okay. Fable hosted lib stdcxx. This is it? Yep. Hang on. Okay. So this is the part that takes almost time. So make dash j, let's go 12 all dash gcc. Now hopefully this will actually not take too long because I'm using 12. Oh yeah, true. Okay. All right. Okay. Now this, yeah, it's taken a while and we're not done with this. We still need to do all targets libgcc, all target lib stdc, whatever, install gcc, install, and all that stuff. Alright, this is... Let me just get some water real quick. Ugh. This is... Alright. So, what I might do is, while we're doing this, I may go over some of the stuff that, you know, I've been doing, and like going over some talking points about the system, and, you know, like what's actually happening and what I've done. So, I mean, first of all, to really do, like, get into this, you need, well, to understand, well, first of all, you need to know, like, what an operating system even is. So, like, okay, well, we're done, so I'll get back into that later after I'm finished doing all of this. So now we go make -12 all target -lib. It was GCC. There we go. Wait. I just did -12. Where the -J12. There we go. Okay, and so now lib this one. Okay. Also, you can keep chatting, like, it's fine. Trust me. It's fine. I was gonna do that, like, later on anyway. I was actually hoping, because, like, this is gonna be, like, really boring part. Because if I'm gonna be honest, in my head, I didn't really want to stream this part of it, which is literally just getting it prepared. So, yeah. So now we go so now we go install -gcc. Probably should have done. Oh, probably should have. Yeah, okay. Actually, never mind. Make install. Wait, hang on. Make install. Yeah, target -lib std ++ v3. Okay, so now we just do that. Now we go Wait, did I do libgcc? I did gcc libgcc lib. Oh wait, dash target dash libgcc. Yeah. So now we've got basically all the prerequisites done. Let's go cd ls sudo rm password. So we have, yeah, look, I don't feel like getting rid of them. I mean, I'm sure it'd be fine if I did, but it's also like, you know, whatever. So now we're back at the top here. I know, very convenient. So now we've got to test this thing. So now we just so now we just need to test it, and hang on, give me a second. So it'll be /cross bin. Okay, this is already seeming like it's working. Dash dash, no, not dash dash, gcc dash dash version. Perfect. So that's i686. That's exactly what we want. And so now I can do this, export path home opt cross. So path. So this basically turns it into having to put in home opt cross bin target to get GCC to work. We can now just do path dash GCC dash dash version. And oh, for fuck's sake. Wait, hang on a minute. GCC. No, hang on, fuck it, what? Oh, hang on. No, never mind. This means we can do, instead of having to do all of that, we just can go target dash GCC dash dash version. And there we go. Instead of having to do all of that, we can just do that instead. So now we have got everything we need. Oh, for fuck's sake. To do this. Not quite, actually. I need Quemu. So, do I have... No. So, sudo apt install Quemu, what was it? Dash system, wasn't it? I'm pretty sure it was Quemu dash system. So first, what I will do is I will show you where the current... First, I need to show where the current progress is by running this thing through Quemu, and then I will go over some of the stuff, like what I have planned for today, what I have planned for the future, and some stuff like that. So I've also got to go over some of the talking points as well still, because what I want to go over is the stuff I've already done. So I'll show you the operating system as it is right now, and then go over the stuff I've already done, which would be the boot process using grub and the multi-boot, and then protected mode and the GDT. then interrupts, like, you know, with IDT and PIC, and then VGA terminal and shell, and then memory management, and then ATA driver and FAT32, which is where I'm currently at. So now we've got this. I'll just clear. Fuck's sake, I need to do this every time. Scroll all the way back up, manually make. There we go. And now if we go ls, we have everything here. One thing we don't have though is we need to get QEMU FAT. So we need to, this is just on my GitHub, we need to create a FAT32 disk image, because if we don't, then it won't be able to boot, because, well, this thing uses FAT32. So we need to do this. Get water, please. So we've gotten that. I'm also going to put that in my little document there. And so now we go make ISO. Alright, perfect. You can't see that anymore. My bad. What I ran was this. This creates the disk image. I'll run it again for you, and if we go into ls, as you can see in there, you have disk.img. It's the second one at the top. That is the disk image. And now what you want to do to boot it is, again, this is just on my GitHub page, is you want to run this command, which boots QEMU in that, you know, i386, because it's a 32-bit system, that is it, and then CD-ROM GordOS.iso, that's the ISO file that we made using make ISO, that's the actual disk image, and then the drive, the disk drive will be disk.img, and yep, we'll make sure it boots off of the disk image, which is the ISO file, instead of trying to boot off of the img file, which has nothing on it at the moment, but we are linking the image file, which is basically the hard drive of the system. We are linking that to the operating system, so the operating system itself can see it, but we're not booting off of it because it doesn't have anything to boot off of. So if we got rid of that, it wouldn't boot. So if we run this, as you can see, we have GNU Grub version 2.0, GordOS. This is exactly what we want, and this is what I have right now. As you can see, PMM initialized, ATA drive detected, root cluster equals 2, reserved sectors, all of this stuff. This is just stuff that I had for debugging when stuff wasn't working properly, but I thought it looked cool. And so yeah, so PMM, that is the physical memory management. ATA drive detected, that's, I'll get into all this stuff later. But anyway, so if we go, we'll just do clear to clear all that, and we go help. So as you can see, the available commands, you have help, which shows this message clear, which I've just showed you. Echo just prints text to the screen. So if we just go echo, nothing happened, because, you know, nothing was there. And then we have touch, which is create empty file, then write, which writes text file. So let's go touch, and we will make it test.txt. And now if we go ls, we have test.txt. Now it is in uppercase, because that's the only way I could really get it to work. I typed it in lowercase, and then it formats it to uppercase. That's how it works, really. And so now if I go ls again, it's still there. And now let's go, what was it? It was not touch, it was cat, wasn't it? Let me it was right, not cat. I don't have cat yet. No, I do have cat. Yeah, no, I have cat. Never mind. Cat, well, I'm fucking... So now we go write test.txt. Wait, no, hang on. Write, let's go hello world to test.txt. Written to, oh, for fuck's sake, hang on, ls. Now we have hello. Cat hello. World test.txt. Great, nice. That's not what I wanted to do. I got the command backwards. rm hello ls. Okay, so now if we go write test.txt txt hello from GordOS. And now we'll go cat test.txt. As you can see, it says hello from GordOS. And so clear. And also, even if we do shut this down, we'll go ls, we still have test. Now reading LBA, I'll get into that later again, but that was again more debugging stuff. If we were to shut this down by closing it and then reopening it, and we go ls, it's still there because it's in the .img, disk.img, which is basically this system's hard drive. So yeah. Oh shit, wrong thing. I can't do Alt F4. Control G. Yeah. So anyway, let's get into some, talking points that I've got here. Okay, so some of the talking points I've got here is like, well, what even is an operating system in the first place? So like, well, it's an operating system. It's, fuck, how do I... So when you press like the power button on your computer, let's say, fuck it. Anyway, when you press the power button on your computer, the CPU wakes up, but like, so it starts executing code at a fixed address, which would be the BIOS basically, I'm pretty sure. And something needs to bridge that gap really, because as soon as you hit the power button, it has no concept of loading an OS really. So something needs to bridge that gap, and that something is a bootloader, and this bootloader that we're using is grub. And so it loads the kernel into RAM basically, and the kernel, if we go just go cd kernel ls, as you can see kernel.c right there, so we'll go nano-l kernel.c. as you can see, this is the kernel right here, and now everything in this kernel is basically all this does is just link to other things really, because that's all I really need it to do. And so it loads this, and because it links to other things, it also loads them as well when they need to be loaded really. So yeah, actually let's see, can I fix this? Can I just go transform stretch to screen? That's not good. That's not good at all. Transform. Actually, I have an idea, guys. Sorry, this is going to go dark for a minute. I may just switch some things around. Like this can go here. That goes there, that goes there. And now screen capture properties, and instead of it being this one, it will be this one here. There we go. Okay. So, wait, no, hang on, fuck it. Yeah, no, I'll be fine. So right here, this is the kernel, and so it just, yeah. So it loads the bootloader in the kernel, and no, it loads. So the kernel, not the kernel, the bootloader loads the kernel into RAM, basically. So the bootloader starts at the fixed address that the CPU also starts on. So it executes code at a fixed address, and then the bootloader calls that fixed address, and then so the bootloader calls that fixed address, and then loads. So as soon as it gets called, because as soon as the address gets called, the bootloader wakes up, and then it's like, okay, let's load the kernel into RAM, and then as soon as that happens, the CPU is basically like yours to do whatever you want with, well, the operating systems, I should say. So from that point on, like, you have raw access to the CPU within your kernel, really. So you have like raw access to the CPU from within the kernel, and so then whatever you write in the kernel will be executed on bare metal, or, well, in this case right now, a virtual machine. Usually I do have some machines that I have tested this on before, but I don't have them. Actually, what I can do right now is let's go into here now, and so I think I found out why it's been laggy and glitchy, because of this thing, which I'm about to show you. So you've pressed the power button, right? That's the power button, let's say. That calls the fuck this. Hang on, let me redo all of this. So you press the power button. That wakes up the CPU, which starts at a fixed address. What is this fixed address? Whatever. Let's just call it. Yeah. So it starts at a fixed address. So does the bootloader, which also starts at a fixed address. It calls that address, and as soon as that address gets called, oh, what the fuck am I doing? Yeah. Sorry. Okay. So, whatever. So yeah, I explained it. I'm not good at this stuff. So from that point on, when it loads, it's yours to do, but like whatever you write in your kernel code, that will happen. However, you don't have any standard libraries, because in C you have printf if you're not writing like anything on bare metal and stuff, you can call printf, and that prints text, really. You'll do something like printf hello, and then the output, you'll run that. You'll also have like whatever, like your variable here, and like not your variable, but your like static void or whatever, like, yeah, you'll have that there. Yo, what's good? And then that's printf. That's a library, right? Like, it's a standard library. It's a part of C. And then the output of that would be just hello. However, with let's just go here. What the fuck? That's not what I wanted. Yeah, there's Josh. There's oops. Anyway, anyway, So that is printf is part of the standard. Printf is part of the standard C library. However, when you are writing your own kernel on bare metal, you don't have any of that. You need to write your own libraries. You have no memory allocator, you have none of that. You need to do it yourself, really. Yeah, so you need to DIY. Do it yourself. What the fuck? Fuck, oh, that's why. There we go. So, it's not that, it's just... Anyway, so you needed to write all of the, when you write your own operating system, when you write your own kernel, you need to do all of that yourself because you're not given any of that. You're just thrown straight into the deep end. And yeah, you know, like you don't have any of these libraries, you don't have any of these functions, you don't have any of that. You don't have any memory allocator, you need to write that yourself. You do everything from the ground up because, yeah. And then with the boot process, like after it has actually booted, you know, you've written your basic kernel, you've got your bootloader sorted, you know, the kernel declares a multi-boot header in boot.c, which is basically, you know, some numbers that grub, which is the bootloader I'm using, recognizes, like, and it's like, you know, it basically declares whether it will be loaded up in 32-bit protected mode. It's like, you do some numbers in there, and you 3 magical numbers, basically. You have, fuck, I keep accidentally, 1, oh shit. Let me just minimize that again. You have 1, which is, I can actually do it like here. 1, which is load, you know, boot, not load boot.s, but like load, yeah, boot dot, no, that's not an S. So it doesn't load boot.s, so hang on. It just load it. It's like load system, really. Load system. And then the second number is set 32-bit protected mode. Oh, that's not how you spell that. Protected mode. So, and then the third one, which is call the entry point to the system. Entry point. Okay, so that is all of that. So that's the basic consensus. And then okay, so let's just go up here. So that's basically, the boot process. Did not explain that well. I'm not good at explaining things at all. And then you have protected mode. So I was talking about, protected mode, which would be like protect mode in the GDT. So with this, when grub, like the bootloader, it hands you control of the CPU, it's already in 32-bit protected mode because grub multi-boot, it's loaded boot.s, and boot.s said, yeah, it's loaded boot.s. So grub loads boot.s, boot.s says, load up the kernel, enter 32-bit protected mode, start at the entry point. Right, and the entry point will be, so it's already in 32-bit protected mode, which is pretty important because in the real mode, like before it was in protected mode, you could only address 1 megabyte. You can only address 1 megabyte of RAM for the entire thing, and with no memory protection. For the entire thing, and then, but in protected mode, memory access, what that does is it goes through like segment descriptors, which is the GDT. Not in the GDT, it's in the GDT, and every memory access is implemented and tagged with a segment. And that segment is like CS for code, DS for data, etc., stuff like that. And then the CPU checks those all against the GDT. So the CPU, so, I'm not making much sense here. It's really hard to me to explain this shit. I'm just, and then the GDT has 3 entries. So the GDT, basically, it's in protected mode, and then in protected mode, GDT memory access goes through segment descriptors that are in the GDT, and then every memory access is, tagged with a segment, and then the CPU checks every segment against the GDT to make sure it is correct. And then the GDT has 3 entries, which is mandatory null descriptor, kernel code segment, and kernel data segment, both covering a full 4 gigabytes address space. Like flat address, right? And then that's the flat model that essentially makes segmentation, whatever, okay, I can't explain that well. It's, and then the IDT and the PIC. The IDT, this is all in my source code, by the way. You can go onto the GitHub and find the IDT and the PIC. This will be in the boot area of it, I'm pretty sure. If I go into here and I just go boot, no, it's not in boot. It would be in drivers, wouldn't it? PIC, the PIC is in there, in drivers, and then lib. That's a string. Where would it be? Display. No, wait, hang on, where the fuck would it be? It would be in CPU. The CPU section would have, it has the GDT and the GDT flush, and the IDT and the IDT flush. Now, the IDT and the PIC is in the boot area, I think it was. The IDT is the CPU's lookup table for like something unusual happened. It says like something unusual happened, the IDT, the CPU would look in the IDT. And then it basically gives instructions on what to do if something messes up. And so it has 256 slots, and the first 32 are CPU exceptions, like dividing by 0. You can't divide by 0, so that's one of them. Page faults and all that stuff. Like stuff you would expect, because CPU can't divide by 0. You can't divide by 0, so why would a computer be able to? And so if your code does try to divide by 0, the CPU will freak out, and instead of messing everything up and crashing and breaking everything, it will look in the IDT. The IDT will be like, yes, you divided by 0. This is what you do now, basically. So that's what that is. As 256 slots, the first 32 are for these types of things. And then the rest are for like hardware and software interrupts. So like each IDT entry points to a handler written in assembly, like ISR.S and IRQ. Assembly is a pain in the ass to write, honestly, it fucking sucks. And they all funnel into, I'm going a second. They all like funnel into like common handlers and stuff like that. So I've told you what the IDT does. That is, like interrupt handling. Like say if something gets interrupted, the IDT handles it, and each entry point, because it has 256 slots, each entry point, each entry, not each entry point, it doesn't have an entry point. Each entry points to a handler written in assembly, and they all funnel into like common handlers that push a consistent registers. Yeah. I can't explain this well. Right, okay, so when an interrupt happens, basically, let me do it this way. When an interrupt happens, the CPU will call the IDT, and an interrupt is like divide by 0 or something like that, or maybe it could be like it can be hardware, and some can be software. Say if a piece of software you've written tries to do something that it shouldn't, that ends up breaking the CPU architecture, not the architecture, but ends up going against what the CPU architecture is capable of, then it will call the IDT. The CPU will call the IDT to see what it should do after that, and then what the IDT will do is it will basically make a save state of the CPU and then reload. Pretty much. Well, it saves and restores it because, well, when you compile code in C, your compiler, it has no idea that an interrupt has even happened, so it won't be able to do it for you. If you're compiling code and an interrupt happens, thing has no idea what to do. The compiler doesn't even know that an interrupt has happened, so it calls the IDT. The IDT will make... So the CPU calls the IDT if an interrupt has happened. It makes... The IDT will be like, this has happened, let's go to before this happened, make a restore point, basically, and then load that restore point, and then basically delete it, because that always happens like in milliseconds, and, yeah. I just got a notification for my own post that I made 2 hours ago, basically. Cool. So yeah. And the PIC, which is the Programmable Interrupt Controller, is a chip that sits in between hardware devices and the CPU, right? So this is an actual, yeah. And by default, it maps hardware IRQs to interrupt vectors 0 to 15. But because if you, the first 32 slots of the IDT are for CPU exceptions. However, the PIC is trying to use the first 15 for IRQ hardware interrupts. which they would collide with the CPU one, so you end up needing to remap it using, what I did is I used PIC remap, which moves IRQ vectors, these IRQs to, instead of, the first 32, it moves it to 32 all the way up to 47 instead of it being 0 to 15. Otherwise, that would cause issues. So, and that is also the standard approach for something like that as well. And there is a bug in my IRQ. On IRQ 7, the PIC can fire, it's not a big one. It's fine. It's just the PIC can fire a ghost interrupt with no real source. So it might be oh shit, something's happened when nothing's happened at all. It can cause some issues, but I'm not too worried about it right now. I'll fix them another time. And when the kernel first starts, interrupts are disabled by default. And then you call them. I call them at the very end of kernel_main, which after everything has been initialized, that's when we call them. So as soon as the kernel has finished getting everything ready, that's when it enables the interrupts, basically. Yeah. And the next part, probably going to be the most exciting part for some people, would be the VGA terminal and the shell, really. Because that's the thing you can actually see. And so the VGA text mode right now, I should probably go over here. You can see what I've been drawing with. So if let's move this over here, and I've also fixed the mouse. I figured out what the issue was. It was just my Wacom tablet pen was just sitting too close to the actual thing. So if we go CD CD V ls, it would be okay. So make clean, actually make clean. CD display ls, so we have vga.c. So let's go nano-l vga.c, and so this is the stuff you actually see. Now you obviously don't see this, but this is what makes up, how I said it had the text box at the start, how you could type stuff in, you could see it, and it just had the green GordOS thing there, and had the purple box with welcome and stuff like that. This is what's doing that. In VGA text mode, which this is get controlled by, I'm planning on doing some other thing. I'll talk about that later, replacing VGA text mode with something completely different later down the line. So it's 80 by 25 character grid, really. So 80 by 25 grid of characters you can put on here, basically. So they're all at memory address 0x. Hang on, let me go. Not Control F. It was Control W. 0x B8. No, hang on. 0xb8. No, okay, never mind. But that's the character grid is at the. It's not in this one, isn't it? No, it's. Yeah, right here. So VGA width 80, VGA height 25, VGA memory. That's where that's the memory address. That's where it starts. And each cell is 2 bytes, really. So each cell, if you think about a grid has cells, each cell has 2 bytes, and then one for the character. like 1 byte is for the character itself. So like A, that's one character, but then another, that's what the A is the character, and so that's byte 1 is character, then byte 2 is color attributes. So, you know, A green, basically, and then that's in, yeah. So, like writing to the terminal is literally writing to memory addresses. The way that I'm doing it here, it's literally writing to memory addresses. So this is to make the terminal scroll, like you saw when I would put in stuff and it would reach the end. Instead of them overlapping or stuff like that, it would scroll down a bit. This is what it did. So it was basically like, here's the height and width of the entire display, which is 80 by 25. And, you know, y equals 0 at the moment, like y equals 0. If y is less than VGA height minus 1, then y plus plus, yada yada yada, terminal buffer, yada yada yada. And then scrolling the cursor left, and then putting characters in the terminal. Now this was quite big. So this is terminal put char, which I use quite a fair bit. Now this put char means put character, and this means in whatever I do, if I were to call terminal put char, let's pull this back up again. If I also have terminal write line as well. These are some functions that I have wrote myself. So let's just erase these. So put char, it's terminal underscore put char. But what this does is this will put a single character. So you do terminal underscore put char, and then you in brackets, you do, and then you'd put one character in there. And now one character is like \n, and that counts as one character because it looks at that type of backslash, not this one. Wait, yeah, no, it is that one. Never mind. So it looks for this \n, not this \. That's the \/ you're more used to, but this \, which you're less used to. So put char looks for that \, sees an n, and that counts as new line, which is a new line in the terminal. You can also do this in terminal write string. Technically, you wouldn't have this second thing. You'd only have one of these, but I forgot to just draw that in, because in write line, you would do these, and then you would write hello there, and then you'd always end it off with a /n, and that's what I mean by you can also use /n in write line, because, well, it'll see that and it'll print a new line, and you always want a new line because then everything will be really, like, it'll be on a single line and nothing will be moving down, and it will be really hard to see anything. So yeah, so that's what that does in this. So terminal put char, it's literally if /n, terminal column 0, you know, so if it's \n, which is the character, then, you know, it will scroll. And as you can, I didn't mean to go all the way down there, god damn it, man. So terminal initialize, terminal selector, terminal backspace, terminal scroll, which is scrolling down. And so I use that for terminal, like \n for new line, I use the scroll to just scroll down one and then put the cursor there. And then if it's T, then that's tab, which you know what tab is. That just pushes the text forward one tab. And then we have update cursor. So update cursor, which is up here, all the way at the start. So update cursor, that was that. It's not blinking, but that's, you can see the cursor when. Oh, hang on, I'm not even there. Sorry, guys. Update cursor. So what I was showing you before was terminal put char this. This is what I was showing. So as you can see, if, /n, I use terminal scroll, which this is terminal scroll here. And you know what terminal scroll does, it just scrolls the entire thing down by one. And whenever I call terminal scroll, it'll just scroll down by one. And that's basically exactly what new line does. It just scrolls down by one. And yeah, now T is tab, like I said, you all know what a tab is. It just pushes it by one tab. And then, yeah. And then, but like, it's like if it is /n, terminal scroll, else if it's /t, tab, and then else, leave it the same really. And then update the cursor right at the end of that. So that just updates the cursor to make sure it's always updated at the right area. So yeah, and then we have terminal right string and terminal right. So terminal right is just for one letter. Terminal right string is for a string of letters. So as you can see, terminal right just does put char, and now this right here, this was an array. Basically an array of I, because I equals 0, so that's basically the same as if I put 0, but not quite, but you know what I mean. So terminal right is just one character, and then terminal right string uses terminal right, but this right here basically makes it support more than just one, character. It makes it support multiple. So yeah, it uses terminal put char here, which, as you know, terminal put char, which is, what was terminal put char? That was here. You can put basically anything in here, although it only really checks for if you've put in this stuff. Now this stuff only works in code, like you write terminal put char or terminal this in the code, and whatever you do will get printed to the screen once you finish compiling and once you've booted. So yeah, we've also got terminal backspace and terminal cursor left, and yeah, because that moves the cursor left. And backspace, well, if you didn't know that, basically just backspaces, which is, where was terminal backspace at? Update cursor, fuck, where was terminal backspace at? There. So I had issues here where I forgot to put the return in, and it would just go back the previous row, so the thing would be here and then it would just go up when I try to do a backspace, because I would hit the delete key and then the cursor would just move up when it wasn't meant to. It would finish deleting everything and then it would go back up and then do everything and then go back up and then do everything. Even if it was blank, it would still just be doing that. So then I had to actually do this. If terminal column equals 0, then just return. And terminal column is, where's terminal column at? Terminal column should be above terminal backspace, right? You would think so. Yeah. Update cursor, terminal initialize. This initializes the terminal. And now, yes, you do have different colors. If we go into vga.h, as you can see, these are all the different colors that we have. So yeah, VGA color black, VGA color blue, VGA color green, 1, 2, 3, 0, 1, 2, 3, 4, all the way up to 15. And then, yeah. Yeah. So that's that. So that is that. And then now we've got memory management. What did you... What? Okay. Anyway. Physical memory manager uses a bit... So let's go. nano-lpnm.c. So it's 118 lines. So I did the terminal VGA a long time ago, and I've gotten a lot better at doing comments in my code to explain things more as this project got a lot bigger. So 1 bit per 4 kilobit page, covering the first 4 gigabytes, and then 4 gigabytes, that's how many pages, and then 128 kilobytes for the bitmap. So 1 bit per page is 1 bit per 4 kilobyte page across the entire 4 gigabyte address space. And that's 128 kilobytes of kernel memory, but it lets you allocate and free physical pages in O time. So, set a bit, mark pages used. So pages, what was it? Yeah, so let's say here you have a book. Oh, fuck. Hang on. Here you have a book, right? Hang on. There we go. That looks like shit. But anyway, you've got... Fuck, you know what? I've got a better way to do this. You have pages. Alright? Different pages. And these are all pages. Yeah? And so each page is 4, not bit, kilobits. 4 kilobits. 4 kilobit. Right, each page is 4 kilobits, and goes on until it covers the first 4 gigabytes. And so whenever a program or whatever needs RAM, this, without kmalloc or whatever, so we have program. So let's say, right, out of this all, we have a page here. It's 4 kilobits. And then we have program. But this program only requires 1 kilobit of RAM. What this, what this doesn't know is that it doesn't know that it needs just 1 kilobit. It only knows that it needs RAM. So it gives it an entire 4 kilobit page, which is 3 too much. So those 3 kilobytes that could have been used on something else aren't, because, well, the PMM by itself didn't know that it only required 1 kilobit, so it gave it all of it. Now, there's something else called kmalloc, which goes in between. So we have kmalloc, and then we have, hang on, then we have the, we have kmalloc physical memory manager, and the physical memory manager, this is the one with all the pages, right? But now, instead of a program calling the PMM directly, it will call, let's just go, hang on, yeah. Instead of it calling the PMM like it was doing before, it will now instead call kmalloc. Kmalloc will call PMM, which will give it the entire 4 kilobit file. So the PMM, so the program calls kmalloc, kmalloc calls the physical memory manager, the physical memory manager hands over kmalloc an entire 4 kilobit file. Now this program, now kmalloc has this big 4 kilobit file, and the program still only needs 1 kilobit. Now, instead of kmalloc giving the program the entire 4 kilobit file, what it will do is it will take a chunk out of it out, right, and give it that chunk, right? And then, so the program that needs 1 kilobit of RAM calls kmalloc. Kmalloc takes the entire 4 kilobit page, cuts out a chunk, gives the right amount to kmalloc. If it needs more, it gives it more. If another program calls kmalloc, instead of it getting an entirely new page and cutting a chunk out of that one, it uses the rest of this one until it needs another one. So it just will, it's more efficient, really. It also does stop some issues, because say with the physical memory manager, it's got 4 kilobit, it's got a bunch of 4 kilobit files, a bunch of them, but say program needs 5 kilobits. PMM has multiple 4 kilobit files, and it can give it both and give it 8 gigs, not 8 gigs, 8 kilobits, but it doesn't. It only knows that it needs some RAM, and it's like, oh, we have some RAM in this page. Let's just give it 4 kilobits. It's not enough, so the program can't run properly. A way around that, obviously, is by using kmalloc, because kmalloc, kmalloc knows. Kmalloc knows how much RAM each program needs. So program 5 kilobits. Kmalloc will get 2 4 kilobit pages, give one whole page to the program, and then split the other one. You know, it will only take out, you know, what it needs. It will just give it the extra 1 kilobit as well. Instead of it getting not enough, it gets the exact right amount every time. So that's what the memory management does. And now on to FAT32. Now this is the most recent thing I have done that just got it set up, which is the ATA driver and FAT32. So if we go cd file system, and then we go nano-l ATA. Yeah, so hang on. No, cd cd drivers, because this is -l ATA.c. It's technically a driver. So this is the ATA PIO driver. Now what this does is the ATA PIO driver talks to the hard disk directly. It's not a file system, it's just what is able to interface between the system and like the software and the hardware basically. It sits in between and translates whatever the hard drive says into, not really, but it makes the system be able to recognize that there is something there. So this, talks to the hard disk directly by reading and writing I/O ports. You know, PIO, because ATA PIO, and the PIO means that the CPU does all of the data transfer itself. There's no like DMA. It is slower, but it's much simpler, and it actually is what works on real hardware. Because I could do DMA, like, which is like digital something or whatever. I'm pretty sure I don't really know anything much about DMA, but it's finicky to get working on real hardware or something like that. So okay. Two concurrent viewers, that's cool. So yeah, so this is the ATA driver. This is what actually talks to the hard drive. So, you know, it sends write commands, you know, ready for the drive to receive data, yada yada yada. So, you know, 16-bit version of inb/outb, which we need because we need the 16-bit version. Now right here, this is assembly. I'll go into that a bit more. So we call it INW and OutW for InW and OutW. So like input, output. We need the 16-bit version for it, so it would actually work properly. And then wait until the drive is no longer busy. We read the status, you know, ATA status. We use the PIC driver for this. No, we don't. We use ATA.h, which if we go into ATA.h here, these are all the, because it talks to it, so it needs like, what is it? Sectors, really, and these are like sector values, I guess you can call them. So ATA data, there's 0x1f0, ATA error, 0x1f1, sector count, 0x1f2, yada yada yada. And then command and status, that's the same thing really, 0x1f7, And for it to be busy, it is 0x80. That means the status is busy. 0x08 data request, and 0x01 error. You know, ATA status error. DRQ is data request. BSY is busy. And then read and write, 20 and 30, read and write. And so if we go back into C, as you can see, is wait for the busy to clear. While status is INB, which is input, which is the, not 16-bit, it's either the 8-bit or 32-bit. Anyway, it was one of the versions of input that we have. It will, you know, it will check the status, and while status and busy, status equals, you know, status and busy, error checking, you know, status and whatever, return -1, return 0. Yeah, and then wait until the drive is ready. So wait for data request, ATA wait data request. So, you know, status while 1, if status ATA error, -1, if status and, you know, data request, return 0. 0 means good, -1 means something's failed. And then send the LBA to the second. Now that's what you saw earlier when it said LBA yada 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 when I did LS. The LBA something whatever. I kind of forgot, if I'm going to be honest. Kind of forgot. Anyway, so send the LBA and sector count to the drive. So it sends everything, all this stuff to the drive. So, you know, it selects 0xe0 LBA to 24 and 0x00f sector count, send the sector count, yada yada yada. You know, this is initialize, which is select the master drive, clear LBA and sector count registers, send the identify command, you know, so we can identify the drive, make sure it is there, and then we check its read status, and if it equals 0, then no drive is present, and then wait for busy to clear, so when it's no longer busy, and then we check if it is indeed ATA, because if this is an ATA driver, we need to check if it's ATA, not AT-API, which is something else completely different. And then we wait for a data request, and then we read and discard the first, like, 256 words of identity data, because when we get its identity and stuff, and then read and whatever, it puts identity data on the disk. We want to get rid of that. So we read it, it's like, okay, so it like reads the identity data, it's like, yes, this is the identity data, we know it's here, this is what it is. Now that we know it's here, we can delete it. And then, you know, wait for the drive to be ready, send a read command, and then wait for data to be ready, and then read the 256 words. Right? And then invents the buffer in the sector, and yada yada yada. Whatever. So that's that. And then FAT32. Now this is, now let's go FAT32.h first. And so FAT32 is the file system. That's what actually lives on the disk. And the boot sector, it contains, oh, let me, no, I can't show you, I don't want to fucking show you boot.s, that shit fucking sucks. So the boot sector contains a PVP, which is, not PVP, BPB. I got that so confused when I was writing the code and I caused so many errors there. It sends a BPP, which is a BIOS parameter block that blocks, not blocks, that describes the disk layout. Right, the layout of the disk itself, you know, cluster size, FAT location, the root directory cluster, etc. And then if we go into, what is it, FAT32 init, which isn't in here, but yeah. So if we, no, don't save that, cd cd kernel nano-l kernel.c, if we go into here, as you can see, we include fat32.h, which is linked to fat32.c. We go all the way down here, and here, where is it? Fat32 init should be here. Yeah, here it is. So ATA init as well. So ATA, we want it to be within ATA init because, well, that means, because ATA detects the drive, FAT32 is the file system on the drive, so we detect the drive, and within that, as soon as it detects, ATA init, as soon as it detects drive, ATA drive detected, FAT32 init, and that equals 0, that means good to go. And then FAT32 mounted, else FAT32 mount failed, and then ATA init failed. And then this is a sanity check for kmalloc to make sure that that was okay, and it was okay. I decided to just leave that debug thing in because, well, I like how it looked when I did it all. So that is that. So now if we go, nano dash L fat32.c. Now this is 679 lines of code here. And this is just for the FAT32. So boot sector 512. Now, arrays. Let's get into arrays because you will be seeing this a lot, right? Boot sector 512. What does that mean, right? So as you can see, convert cluster number to LBA address, cluster to LBA, mount next cluster in the chain from fat. Right value of fat given and cluster entry, whatever. So find a free fat cluster, yada yada. It's, yeah. This is just for the file system, but anyway. So as with, you will be seeing arrays pop up. But what is an array? So you saw boot sector, and then it had this 512. You saw that. What does that mean? Right? Like, so basically what that is we have uint8, which is a value. So uint8, wait for it, 8 underscore t, that's a value. And then uint8 underscore t boot underscore sector 512. So what that 512 does is So what the 512 does is it basically is asking for 512 of uint8, values. It asks for 512 of them. And, whatever. So that 512, instead of having to write uint8 512 times, you do this, well, not that, but you do that instead. Give it a second. Nope, that's not what I wanted to do at all. This piece of software ain't the best, hey? But, it works. Whatever works. You do that instead of having to write uint8 512 times, which would be an absolute pain in the ass. So, think of it as like a street with 512 houses, right? Right, you've got road here, and then more houses, like, yeah, well, 512 houses. labeled from, you know, this house is house number 0, house number 1, house number 2, ... house number 100 from here, whatever, who cares, right? It is 10, 12, all the way up to 511, because, well, we have the 0 there, and technically that 0 counts. So all the way up to 511. And each house holds 1 byte. Now let's think of 1 byte as 1 person, right? You can't see that because my face cam is in the way, but anyway, that says 1 byte there. That says 1 byte, trust me. So let's say, like, you are house number 0, like 1 byte. And the name boot sector is just the street name. So UINT 8 is, let's say UINT 8 is like the town, and then boot sector is the street address. And then it tells you house 0, like the 512. And so it like tells you where house 0 is, and then from there you can find all the other houses, basically. And then 512 is just there, right? Yeah, that wasn't really a good explanation. I thought it would be. It kind of was, but anyway, you get the point. Instead of writing UINT 8 boot sector, UINT 8 _ T boot _ sector 512 damn times, you just write that 512 thing, you know, which is an array. And so the 512 is there because, let's go back to here, show them behind the scenes of this thing here. Static, right? So it doesn't move from here. That's what static means. It's fixed. So the 512 is there because a disk sector, one disk sector is exactly 512 bytes. So that's what I mean by boot sector. Hang on. Anyway, so what was I? So a boot sector is exactly 500. Not a boot sector. One hard drive sector. One sector on a disk is 512 bytes, and it's not like a choice we made or anything. Like, it's not like I chose it to be 512 bytes. It's just a hardware fact. And the ATA driver, not the ATA drive, because we're no longer on the ATA drive. This is FAT32 itself, the file system. So, hang on. Okay, so it's just a hardware thing. And so the ATA drive, the ATA drives, because right now we're using ATA drives, that's all we have access to, right? In virtual machines anyway, and most drives are ATA. They read and write in 512 byte chunks. Kind of like the physical memory manager. You know how it was 4 kilobytes each, passing out 4 kilobytes. That's kind of the same thing, except for it's less, whatever, like 512 bytes, 512 bytes. Everything gets 512 bytes, you know? So, and so, you know, like, the buffer, which is the raw sector buffer for the BPB, which I kind of talked about, but it's a piece of, hard to explain, for me anyway. so the buffer, my buffer has to be exactly that size, 512 bytes. To be able to receive 1 byte, it has to be the size 512. And say later on, let's go boot underscore sector 11. Not here. Did I really not do any boot sector things in here? Buffer 12, right, yeah, whatever. Buff I++. And that's the same thing here, right? Buff I++. That's also an array, I++, because I equals, what did I equal here? Oh, simply like offset +3, offset yada yada, buff, offset, buff, offset, buff is buffer, by the way. Yeah, I equals 0, I++ basically means add 1, so I equals 0 right now. And I++ basically means add 1. So buff I++, so buff 1 equals 0, whatever, like, yeah. Is that meant to be minus minus I or I minus minus? I think that might be meant to be I minus minus, but it seems to be working right now, so I'm just going to leave that the same. I will mark it, maybe meant to be I minus minus, but it works, so I'm leaving it, you know. And then forward declarations, you know, just forwarding things, because if I didn't, then it wouldn't work, because there were some things that worked before others. Yada yada yada. Sector 512. 8 sector 512. Yeah. So say if I write boot sector 11 at some point, which I know I have written in some code before, which is boot underscore sector 11 sector, and then in the array, the square bracket array, I put the 11. That's basically saying go to house number 11 on the boot sector string, and then that happens, and so that house just happens to be where the FAT32 PBP is living. Basically, it lives at house number 11, and so when you write, like when you call it, it's basically like, hey, get to work, you know, get to work FAT32 PBP, kind of like that. When you, yeah. So now one thing you've probably seen is you've seen UINT 32 underscore T and UINT 8, and you will also see UINT 16. So UINT 8, UINT 16, UINT 32, this constantly comes up. It's always there. And in normal C, you would write int, which is integer. But for this thing, it's a bit vague. Just a normal integer is just vague, and an integer is like a number or something. And its size depends on the compiler and platform, like how big the integer or whatever is. Depends on like the compiler, the platform you're compiling for, yada yada yada. But sometimes, like when you're like directly talking to hardware, being vague is not good. You need to be incredibly accurate. If one thing is off, everything breaks. So if you tell the disk controller there are here's a 4-byte address, like you tell the disk controller here's a 4-byte address, but then you put an int instead of like uint or something like that, the int is actually 2 bytes or something like that. You're just basically just putting absolute garbage on, and it'll break everything. And so uint 8 is, you know, exactly 8 bits, which is 1 byte. Holds 0 to 225. So yeah, and then uint 16 is 2 bytes, you know, exactly 16 bits, 2 bytes, and then holds 0 to 65,535. and then you have UINT32, which is exactly 32 bits, which is 4 bytes. It's exactly this, by the way. It's not like whatever, because with INT it could be like, with normal INT it could be, you know, depending on what the compiler wants, really. And the compiler doesn't know we're doing, and the compiler doesn't know that we're trying to be incredibly exact with these things, because the compiler doesn't know what we're really making. It just compiles the code for us to do what we want with. So it'll basically just determine, if you use INT, oh, it should be this many bits, when in reality it shouldn't be that many bits, it should be this many bits instead, but the compiler thinks it should be that many bits instead, so it does that, and then that causes errors. So then UINT is basically like UINT 32 underscore T, 32 bits. Whatever you put in there is 32 bits. So UINT 32 underscore T fat offset. So fat offset, that it's like, I've called this thing it's called fat offset, and fat offset equals cluster divided by 4, but because I use UINT 32, it is only going to be 32 bits. Whatever this is, 32 bits. Exactly 32 bits. No higher, no lower, exactly 32 bits, no matter what. And the U means unsigned. So it can't hold negative numbers at all, but it can hold double the positive range, right? Compared to like a signed type of the same size, right? But signed can go negative, but it can't go as high positive, basically. And I'm not really working with that many negative numbers. When I am really working with a negative number, it is return -1, which usually means return an error, right? So if if ATA read fat sector 1 does not equal 0, which 0 means good, in a lot of these cases, 0 means good. If it doesn't equal 0, return -1, which means error. Return an error code. And so UINT 8 underscore T, 1-digit hex number. UINT 16, 2 digits. UINT 32, 4 digits. So say like when you're reading hardware documentation and it says something like field at offset 11, size 2 bytes. You know what holds 2 bytes? UINT 16 underscore T. Double check myself there. So okay, so pointers. These things trip people up. A pointer, like the star, really. You see this a lot as well. Let me see if I can find an example in here. Shouldn't be too hard. All I should really need to do, Control W, and I just did this. Yeah, boom, pointer. UINT, pointer. It's just a variable that holds memory rather than a value. That's all it does. The star means this variable, UINT 8, right, holds an address. Like, this variable holds the address of UINT 8. So buffer doesn't contain a character, it contains a location of a character. So UINT 8, so this holds, yeah, the variable holds the address. So this is basically telling me it holds the address of a UINT 8 variable. So buffer isn't a character itself. Buffer equals the location of a character. So when buffer gets called, instead of it calling a character, it calls the location of the character. That's a very thing. Like, yeah. So as an example, like I I haven't actually gotten onto any of the actual programming that I'm going to be doing. I've just been explaining this stuff. I will get into that, I promise. Yeah. I'm just going over this stuff real quick. But not real quick, though. So, yeah. It's like the location. And so, for example, when we were in the VGA frame, like VGA.c, 0xb8000, that's a literal memory address right there. And that's where the VGA frame buffer lives on x86 hardware. And by assigning the address to a pointer, instead of typing in 0xb8000 every single time, I assign it to that address to a pointer. So that way I'm telling it, when I write this through a pointer, I want the bytes to end up at that address. And since VGA hardware is, watching that region of memory, whatever I write there appears on the screen. So instead of it writing, just, yeah, whatever, yeah. I hope that explained it. So, yeah. And now, structs. Woo. Are they in here? Because they're another thing I want to go over. Struct. No. Anyway, so it's just a way of grouping, like a struct way of grouping variables together and, giving them a name as a unit. Instead of just all individually, it structures them together, really. And then static variables, so static int instead of just int, static int. The static keyword does different things, depending on where it is used. It pretty confusing, but you get the hang of it. Inside a file, static basically means that the variable is private to this file. So only this file can read it, really. So any other .c files can't see it or accidentally override it or something like that. And so in PMM, actually, the bitmap is a static because nothing outside of PMM.c, nothing outside of that, PMM.c will get called. That's the only time that bitmap will ever be told by PMM.c itself, because nothing outside of it should touch it directly. It should touch it through PMMC. The exposure is controlled access through PMM allocate page and PMM free page, which are the not variables, functions that I have given the kernel, the system, really, to be able to access it outside of PMM.c. But when you call PMM_alloc_page, that talks to PMMC, PMM.c, and then that's what is actually, yeah. And so now we have macros, which, as you can see, #include, that's not a macro, but if we, I don't want to save that, if we go #h, as you can see, #define, #define, yeah, it is a text, fat ATTR system. What this is, it's a text substitution. So that yes, it's a text substitution that happens before the compiler even sees the code. So before the compiler has even seen the code, this. Every time the processor spots, not the processor, the preprocessor spots something like fat attr read only in my source code, it replaces anything to do with fat attr read only to 0x01. So whatever is in the code, what that'll do is that will replace whatever is in the actual C code that says fat, and also same with attr hidden, system, volume ID, whatever, all of those numbers next to it. In the code, it won't, in the compiled code, it changes every single one of those to the numbers next to it. This is just a way to make it easier on yourself when you're doing read-only all the time, when you're writing read-only all the time, when you're writing volume ID all the time, when you're writing archive all the time. Instead of going 0x20 or 0x whatever and trying to remember all these numbers, and especially with the longer ones like fat32_free or fat32_ EOC, instead of having to put in 0x0ffffff8 every single time you want fat32_ EOC, you just type in fat32_ EOC, and then the compiler will go see that you've defined it to 0xFFF8, and then physically replace it with the exact thing you want. It just defines what it's meant to be. So yeah. Yeah. And so then that is macros. That's what that was. And now bit operations. It's really tricky for me to explain this live. Like, I do have some notes that I've made for this. I wasn't expecting to spend literally 2.5 hours just explaining things. Also, is anyone actually still here? Because it says I have 2 concurrent viewers, but the chat's been quite dead. Yeah. But anyway, so bit operator, it's really hard to do this live. Explain it live, but because it's like really clever and shit. I don't want to toot my own horn here, but I'm not the one who actually fucking defined these things. I'm just the one who learnt it. Whoever actually made bit operations. Hey, hello there. That's good to know. That's good to know. How are you enjoying this so far? Do you want me to just hurry the fuck up and get in with the code, or are you happy with me explaining this for a bit longer? Right. Okay. Well, you can talk more if you would like. It would be nice to have some feedback on things every now and then, or like if you have any questions, say them. But yeah. So anyway, bit operations, they're hard to explain. Not hard to do, I mean kind of hard to do. It requires some maths, but it's hard to explain. You know, you like listening, that's cool. Is there anything you have any questions with? Like anything you need more? That's okay. Anything you need like more explanation with? Because I'll try to, or like, whatever. Okay, so with that question there, if mayonnaise is an instrument, I'm gonna have to say no on that one, but horseradish could be. Yeah, I think so. I think so. Also, oh god damn it, man. I had this set up to goddamn have these on for the entire stream, but I completely forgot to even put them on. How does this look? Yeah? Do I looking fucking fire over here? Okay. So, what was it? Bit operations. So let me try to find somewhere with bit operations. Let me just go. Oh, fucking. This has no, not this one. .c. This has to have like bit operations in it, right? Like, there's no way this doesn't have bit operations. It goes sometimes, so you could probably make it. Okay, what do you mean by it does that? Like, the audio is a bit. Also, don't apologize. PMM. So, let's go to the PMM. So CD memory. So nano -L. Now, a lot of people will get mad at me for using nano as my text editor, but it's like just something I like using. It's simple and it does what I need it to do. It might not be the best, but I know how to use it. It's definitely not the best, but it's also definitely not the worst. It also just comes with the system. So PMM stores 1 bit per page, right? So this right here, yeah, this is a bit operation. So it stores 1 bit per page. So to pack bits into bytes, each byte in the bitmap holds the state of 8 pages. Does that make sense? Probably not. It was really confusing for me to figure out the first time as well. Like, Jesus Christ. Good to know that. Anyway, so this is like absolutely really hard to do it. So, you know, the PMM stores 1 bit per page. I'm not going to draw it out because I have no idea how to. 1 bit per page. And then to pack bits into bytes, because we need it into bytes. Each byte in the bitmap holds the state of 8 pages. So 1 bit per page. 8 pages, 1 byte, basically. Kind of. Yeah. So page, so bitmap, and then this is the, I literally was just talking about it, so it's the array. Fucking hell. So this is the array here. So page /8 means, you know, which byte does this page, like which byte does it live in, right? That should actually be a space there. And so hang on. So which byte does this page's bit live in? What the fuck? Did I? No, I didn't. I just jumped to the end. I thought I just broke something there. No, I did. Where'd my egg go? Wait. There. Okay. And so like integer division, so so it's like integer division, right? Really? So byte this page's bit live in. So integer division. So pages 0 to 7 are in byte 0, and then pages 8 to 15 are in byte 1, and then, you know, so on and so forth, right? So pages 8 to 15, page /8, right? And then page %8 over here is which bit within the byte, really. So like the remainder of the dividing by 8, right? So page divided by 8, right? It's the... I told you this is really hard to explain, especially when I'm not the best at math and stuff like that. Like, I have gotten a bit better just by doing this sort of stuff, but I'm still not the best. I'm also not really that good at explaining these things. But anyway, this is why I wrote a little bit of some like pointers to help me out when I'm live. So yeah. So there's like which bit within the byte, so it's like the remainder after dividing by 8 gives you the position within the byte, you know, 0 to 7. Right? And then this here, which is 1 less than, It's shift the numbers left by that many positions to create a mask with exactly that bit. So if the bit position is 3, you will get 0, 0, 0, 0, 1, 0, 0, 0. 0, 0, 0 at the end. 3. So yeah, basic math I'm not good at, but this thing I'm also not good at, but I feel like I'm slightly better at this sort of thing, which is like, it's confusing. Like, I remember like, no, it was funny. But I remember like, I think it's on the Baking Bad channel. It was like 2 + 15, and I was just sitting, like something like that, and I was just sitting there like, fuck, what do I? Huh? And then shit like this, which is literally like, you know, page divided by 8, you know, what byte does the page live in with integer division, so pages 0 to 7 are in bytes 0, 0 to 7 are in byte 0, and then pages 8 to 15 are in byte 1 and all that stuff. So I calculate that, and then I figure out that I need page to be divided by 8. And then with this over here, I need to like, which bit within the byte does it live in? So the remainder of the dividing by 8, which gives me the position of the byte. So I also figured out and did that to figure out that I also need an 8 there. Which wasn't that hard, since the this is the max amount of pages, really, which, as you can go up here, max amount of pages, divide by 8, right? And so, yeah, I needed to figure out that 4 gigabytes, because I knew that it was meant to be like 4 gigabytes for the entire thing. That's true, that is true. Math is harder when you're on the spot. But anyway, so it's like, it's meant to always be like covering the first 4 gigabytes. So I know that one page is 4 kilobytes. So it was 4 gigabytes divided by 4 kilobytes. That gave me the amount of pages I needed. And so then I had to divide it by 8. That equals that many bytes, which equals 128 kilobytes, which is how much I needed for the bitmap. And so I knew that that divided by 8 was that, so I knew that page divided by 8 would be the correct answer there. And so then this here, this is shift the number left by 1 to create a mask. Oh, I already told you that, didn't I? Yeah. Shift, yeah, to create a mask, so then, you know, the bit positioned by 3, which is at the end. Yeah. So if that was a 2, instead of it being 0, 0, 0, 0, 1, 0, 0, 0, again 0, 0, 0 at the end, it would be 0, 0, 0, 0, 2, 0, 0, 0. But that would be incorrect, that wouldn't work, that would break. And then this over here is the OR gate. So, you know, OR that mask into the byte. So, yeah. Which sets that one bit without touching any others. So this basically is like, all this sets the bit, doesn't touch any other bits. And this one's and this, so it sets it and it does touch some others. And yeah. Yeah. So yeah, that is that. And so now it's time to get into my favorite part. Assembly. I hate this thing. So we go here, let me just clear the screen, go ls again. Assembly, that would be in cd boot, would it? No. Boot.s, so nano-l boot.s. This is assembly right here. So this is the closest thing you can get to machine code without actually writing machine code, basically. So this is, yeah. This isn't actually really good. I've got to have more, where would it be? Okay, CD, CPU. It would be in... Okay, no, actually, for this little thing, let me go to cd kernel, nano-l kernel.c. If we go all the way down to here, you have ASM volatile. So this lets you drop raw assembly instructions into the C code. Because this is C right now, but as you can see, STI and HLT down here, that's raw like assembly, right? And so that the volatile right here tells the compiler, do not optimize this away, because it might the compiler might try to optimize your code, and it might get rid of this, unless if you tell it volatile. So like the compiler is normally allowed to reorder or eliminate or like cache things that it thinks it is redundant, but for hardware instructions like HLT, which is halt, no, I was being sarcastic. This thing sucks. Assembly. I mean, it's cool to learn. It's cool, it's cool to like figure out that you can just do this stuff. But writing this stuff is, it's a pain in the ass, especially because you don't know if you've made an error until not only after you've compiled it, you've tested what you want to test. And I'll show you what the testing process is like when I start actually like writing the code, and doing that stuff. So yeah. Anyway, so halt, HLT, halt literally means halt the CPU until the next interrupt. So this, what I mean by stops my CPU from running away is, cause sometimes you can have CPU run away. This is directly in the kernel as well. So as you can see in this entire block here, kernel main, you can tell because of the curly brackets here, you have one there. Yeah, curly brackets, they're quiet. It's like a chunk. You have the opening curly bracket, you have all of this code, closing curly bracket. It's right at the end. You have halt. So that is in case if it goes through all of this, which is the GDT, the PIC, the IDT, the terminal initialize, which that should be right at the top, shouldn't it? Yeah. Terminal underscore initialize. Was it? Don't save, go back into it. Let me... It looks like I'm put together. Sweet. So this should be terminal underscore initialize. Do that. Get rid of there. That should be right at the top. That initializes the terminal. The terminal is what you saw when I booted the thing. Anyway, so halt, in case if it goes through all of this without, you know, like repeating anything, without redoing any GDT initializations or kmalloc or anything like that, or like without anything being called again from the terminal, which is almost like if nothing gets called from the terminal, nothing gets called from magic, nothing gets called from the GDT init, nothing gets called from the PIC remap, nothing gets called from IDT, nothing gets called from this, nothing gets called from that. This, for some reason, this will get called, but it'll get called once. And so after it's get called, it will move down to this. If that never gets called, this will get called, but if ATA init never gets called, then it will, obviously, ATA fail, that'll run once, and then this will also run only once. And then if that only runs once, and that only runs once, that only runs once, and this, for some reason, only runs once, then halt. And what that basically means is it stops the CPU from running off, doing something that it shouldn't do, putting garbage in places, and doing that stuff. Instead of it doing that, it will halt, and it will wait for the next interrupt. So it will go all the way back to the top and just wait. It will sit there at the halt until something else happens. And then STI, which is here, there's also another one, CLI. It's enable, STI enable, and CLI disable interrupts. And so the thing is, if volatile wasn't there, it would be catastrophic, right? Volatile is the way of saying this has side effects you can't see, leave it alone, right? The side effects are meant to be there. And with the halt as well, if that wasn't there, just at all, even if it did get all past there, even if it didn't get past everything, if the halt wasn't there, the CPU would pin itself at 100%. That does nothing between interrupts. When it needs to do something before interrupts, it needs to wait for interrupts. This halt will always get called. The main thing it's meant to do is just stop the CPU from just continuously spiraling. If it gets past all of here, then the halt is more important, which it should never get past there. But again, if it does, then it will halt and wait for the next interrupt, as well as it will always just halt and wait for the next interrupt at any time, really. Otherwise, the chip would get, if it was on real hardware, the CPU would get incredibly hot until it crashes. It also prevents, helps power consumption and whatever. On a virtual machine, it doesn't really matter as much, although I do run this on real hardware every now and then, and I do like testing it on real hardware, and even if it wasn't a virtual machine, it would be running very, very slowly. It would be taking up a lot of resources on my main machine. Yada, yada, yada. Anyway, that is that. That is all the explanation for everything. Now, I think it's time to get started. Now, at the end of this all, I can give you guys some resources, give out resources in case you wanna wanna do stuff like this yourself, really. Yeah. Okay, so you guys ready? Alright, hang on, let me just... Okay. Just making sure everything is going good. Before I get actually started in everything. So what we're going to be working on now is renaming files, because right now we can't rename. So hang on a minute. Yeah, all right. So I think I should do a quick explanation on what this means with renaming files. So basically, I don't think I actually really need to do this, do I? You have something called, let's name it, test.txt, right? No, okay, actually, better idea. You have, let's say, you have story. Let's say you're writing a story, and this is the 1.0.txt. You've written a story, you think you're done, you name it 1.0.txt. Right? But it turns out you're not done, you want to add more. Instead of creating an entirely new one and copying and pasting the contents, you just rename it from that to story 1.1.txt instead of needing to, create an entirely new separate file. Pretty self-explanatory, but that is what we will get started on. Oh, what the fuck? I know. It's also the first time I've used this drawing tablet in a really long time. And also, even not on a drawing tablet, my handwriting is utter shit. So, yeah. Yeah. So anyway, that is what we'll be doing. And so let's go into cdfs ls. So nano-l fat32.c. And so we will put this right after delete file. Oh, hang on a minute. Oh, I need to get better at like swapping back. Yeah, I can definitely give you a go on it, like 100%. Alright, so after delete file, so let's go Control W and we'll just go fat32. So Control W on Nano is for search. So, and down at the bottom it says search fat32 delete underscore file. And so right after fat32 delete file, which is right here, because that's where the ending closing bracket is for it. Let's just go here. There we go. And no, I'll get you. So we'll go int fat32 underscore rename underscore file. So this is what we're going to be calling this function, rename file, if you didn't know. And so now we'll go const char character and do that. Right? And so old path, which is a variable we've just made. We've made the variable called old path. Now old path is, whenever we say old path, we refer to a real memory address. And that memory address, the real memory address, is the same memory address as the old file path or file name we had. And so the bracket here, not bracket, comma to split it for the new const char, again, this new path. And so if not old path, not new path, return -1 as an error, right? And so now we go uint 32 underscore t dir underscore cluster. So this is another variable we've made. Now this variable equals root underscore cluster. Now I'm pretty sure root, yeah, so as you can see, dir cluster equals root cluster. We have it here. However, this is in a completely different static, so we can make another one again, basically. Because most of the time you can't have multiple variables with the same name. But we can right now because they are in completely different, well, let's call them blocks, really. They can talk to each other, but not really. And if they don't really talk to each other, like, it will give you a warning, but not an error. But we aren't linking rename file and create entry together, so it is safe for us to remake directory cluster and root cluster. uint8 underscore t, remember that thing, the little star guy, buffer equals kmalloc, now remember kmalloc, and now we'll go to sectors per cluster. Now this is actually something we are calling. Now remember this, every cluster, it was 512 bits. There we go. And now, if not buffer, or buff, if you're not buff, please leave, return -1. And then, while star guy needs a name, he's got a name, is the star guy. He already has a name, actually. No, yet. I don't know what you're talking about here. He's already got a name, and his name is a pointer. His name is Pointer, right? So while dir underscore cluster, well, by then? What do you mean by? Equal to 2, and dir underscore cluster less than fat32. I'm gonna look sick as fuck with these on, hey. Shh. Huh? What are you? Okay. I don't know what you're on about. Fat32 underscore EOC. Oh no, EOC. If we cluster underscore cluster buff does not equal 0, so if read cluster, and then we've declared this inside read cluster, if read cluster does not equal, damn, okay, I can't actually read my messages, my glasses ain't picking up, so like, if read cluster does not equal 0, we cause a break. Now, it doesn't mean the code breaks, it just means we go back. Oh, okay, alright. Break, and then uint 30, that's 32 underscore t, entries equal sectors underscore per underscore cluster. So there's entries, you know, sectors per cluster. 512, because again, as you know, 512 sectors, yada yada yada, 32, right? Bam. Because uint 32, uint 32 underscore, and that's not underscore underscore t, I. that's not an I, that was a 1. And then now for I equals 0, I is less than entries I plus plus. Now let's just scroll down a bit. UINT 8 underscore T pointer to E equals buffer plus I 32. That seems correct to me. Yeah. Now, if you're happy and you know it, clap your hands. E, and now we're not that. We're going to have a I know the name. I don't, but I know. Array. Yeah, no shit, Sherlock. If we're gonna have an array, we're gonna have an array with 0 in it. Boom. Equals. So E is a pointer. E equals buff plus I32. Well, not I32. I divided by 32. Yeah. Wait, no, multiplication. The slash is I. Wait, yeah. It's also used for multiplication. So I multiplied by 32. Yes, that is what I want. So if E equals E with the array 0, x 0 0 as the pointer, yeah. Then yes, because go to not underscore found. And not found, that's what I have in here. If it's not found, it will say not found, really. I'll be like, we haven't found your shit, man. You're just lying. You're just making some shit up. If UINT 8 underscore T E again. I know what it's called. Array. Fucking hell. I know what it's called, man. Trust me. So yeah, if E0. Okay. Anyway. E at the array of 0. T A under T. Now it would be 0x E5. Yeah. Yeah. Now let's continue. No, not continue. Yeah. Now. Yeah, UINT underscore T. Hang on, let me just. Yeah. UINT underscore T. ATTR for attributes. Yeah, equal. Bleh. Attributes. Can you guys hear me all right? Like, do I need to turn up the volume or move the microphone closer or something like that? Or how many people are here? Still 2. That's fine. That's fine. That's fine. Foot. Nice. Feet. ATTR equals E, and then an array, I remember the name, because I know what they are, of 11. Yeah. Yeah. And then if, yeah, we can hear you, sweet. ATTR equals, it's 0x0f, should be anyway. Yeah, 0x, wait, so, continue 0x e5 up there, and then e11 if ATTR 0x0f. Zero x zero f, yeah, and then ATTR. This one will be ignore that. 0x08. And that will also be continue. Yeah. And now this will be to build the file name. So we'll go down here. Again, just give myself some more room. Sure. Name. Now we'll give it 13. Int n. Now I'm using integer for this one. Just not integer. Just normal, not UINT. Because this one, it's not really all. Like if it's it doesn't matter as much. Int j. We'll just make j. We'll define how much j is here with the for loop. So j equals 0. So we've made j here. Now we've made j equals 0. Now there's meant to be a space there. And if j is less than 8, and e, which we will give an array of j amount, so 0 technically, and e does not equal that character of nothing, j++, which in return will up e, and then name n++. I think that's, which equals e, which will also again give the array of j. Now n++ we declared a while ago, way further up. Yeah. Yeah. Now, obviously do that. Now if, another if statement, no, not another, another if statement. If e, and instead of giving it an array of j, we'll give it an array of 8. That's 9. No, that is 8. Yeah, I'm correct. If e does not equal empty character. If e does not equal that, name, which is still with the array of n++, so it goes up, equals e, and we're gonna give the array of j again. We missed our bestie j. There we go. And now, inside the if statement, we will have a for loop. J equals 8. If j is less than 11, and E with the array of j amount. Yes, totally. Does not equal empty character. No, I need to have a space in there, otherwise it won't be declared. We obviously do j plus. There we go, and so now name, that's an mn plus plus equals j, no, not j, e with the array of, fuck, e with the array of j. Yeah. If e now with the array of 8, because j equals 8, j plus plus, yada yada yada. Well, the array number of 8. If it doesn't equal, that's what the exclamation mark means, by the way, an empty character, name again, and thou this with all n++ arrays will equal a not empty character, one with a full stop. Hang on, give me a second. Yay. Okay, alright, let's get back to this shit. Wait. Yeah. So, it's no longer empty, it's a full stop, and that's what you mean, like, .txt, kind of like file name type shit, you know? Like file type. Okay. File type. Yeah, and so it no longer equals. Yeah, so. What is. Another for loop in this bit. For. He's a jolly good fellow. Anyway, for. What was I doing here? Yeah, j equals 8, as we already have discussed up here. It still does equal 8. We haven't changed how much j is. I guess I did say it was so much sass, huh? I need to watch that back, eh? Okay. So j equals 8 still. It still equals 8. Yeah. J less than 11. Because, you know. Am I going mad? I mean, not quite. yet. Starting to, but I'm holding it together. And E with, again, the variable, not variable, fucking array of J does not equal empty char J plus plus, literally the exact same thing as further up, like exact same thing. Wait, hang on a fucking. Hang on, just thinking here. Looks fire. Hey, thank you. Just wait until it actually fucking works. Let's see. So name 11. I mean, that's the same as up there. Yeah. I mean, will that work? Less than 8. Well, hang on a fucking minute. Hang on, wait. Hang on, no, hang on. Have I just doubled the entire... Wait. So, hang on. So up here, for J equals 0, less than A, and E, J does not equal that J plus plus. Name N plus plus E, J. If E8 does not equal blank character, name plus plus. Name, wait, name, yeah, if E8 does not equal blank character, name plus plus. I'll fuck this entire thing up basically, hang on. Wait. Hang on, where am I? Yeah, I need to do this all manually now. There, okay. That's annoying. How did I fucking manage that? That's like... Yeah. So, if E8 does not equal that, name N plus plus equals... Especially that. I'm pretty sure. Yeah. What the fuck was I on? And so now, for... Yeah, I just realized like that wouldn't have worked at all. No. And so for J, again, another for loop. Yeah. Yeah, that is true. I've been at this for... I'm going to get this part done. I'm going to get renaming files done. And then I'm probably going to call it for tonight. Who knows? Yeah. Unless you guys want me to keep going, then I will. But I'm definitely going to get this done, up and running. And then talk about some future plans for the system and get it working. Yeah. So for J equals 8. Wait. Yeah, J equals 8. J is less than 11. And E with that being J in it doesn't equal blank character J++, and now we go name n++ equals E J. Yeah? Yeah. Name n equals boom /0, baby. So now we do case insensitive. Hang on. Hang on. Oh. Oh, okay. Alright, so this will be case insensitive compare. So basically that just means it doesn't matter if you have caps lock on or off. If it adds up, it adds up. Say like you have text.txt, but it's saved as text.txt and all of them are capitalized, and you not remove it, but you change the name. But you go like input file text.txt, but you put it in lowercase, it'll still, yeah. So match equals 1. Yeah. For J equals 0. Name, not Bane, name the array of J. Old path with the array of J, J++. If to underscore upper name J, oh yeah, does not equal to underscore upper old path, the array of J, match equals 0, break. Yeah. Right here. if match int ni. Now this will be like space add name field, like padding type thing. Hands itchy. Okay. Not for j equals 0. J is less than 11 if j less than 11 j, oh not kj, j plus plus. E with the array of j equals blank character, so that's like space. And so now we write new base name in uppercase, right? Because this is what this thing will be doing. It'll be doing it all in uppercase, basically. Because yeah, if new path with the array, oh that's not an array, array ni equal parenthesis. Oh shit. There we go. Ni plus plus j equals 8. Oh, hang on. Yeah. You always need to have this little guy right at the end, otherwise it breaks everything. Is just to let you know that one line is finished. Well, not let us know, let the compiler know one line is finished and to move on to the next thing, otherwise if not it'll just think everything is one block and that's not good. That's really not good. So j equals 8, and so now while new path ni, and then, no that's not end, and then j is less than 11, e j plus plus equals 2 underscore upper new path with the array of ni plus plus. No, that's I want ni plus plus. There we go. And so now let's just write underscore cluster buffer, call white cluster. Now we go k-free, which is like kmalloc, except for it frees up RAM that is no longer in use instead of giving stuff that needs RAM use. Zero. And so it should be here, right? Because that second one would be this big for loop right here. So then, yeah. So then outside of that for loop, like here, I want dir. cluster equals fat underscore next underscore cluster, and now we obviously got dir underscore, no, that's plus what the fuck underscore cluster. Do that. Oh, that's an L. Oh god. And so now not underscore found k3 buff return -1. Okay, and so now we go fat32.h just to update this. So right here underneath delete file, right here we go int fat32 underscore rename underscore file, just so everything gets pointed in the right area and everything can get read correctly. That's really what the point of the .h files are, right? To define things and to make sure things get pointed in the right direction, right? Const char with a, not har, char with a pointer, old path, const char with pointer to new path. And that's an L again. Save that. And so now I need to go into cd.cd kernel ls, there should be shell.c, so nano-l shell.c and shell.c. This is how everything, I'm heading out, this is going really good, have a good night, you too, man. We're right at the end of this though. All I need to do is add it into shell, and yeah, I'm like quite close to finishing up. If I get like compile errors and stuff, I might actually still call it. I went on way too long explaining things than I should have. This is how all the commands get written as well. Like this is how I implement all the commands into the shell. So right at the end, the last one is rm, and shell execute is what actually executes them. So if we go here, we'll have rename, so static void, no, void cm, we're going to name it cmd underscore rename because that makes sense. Const char with a pointer to arguments, and we'll just push that down, and now we'll go if a args, and then point it to args equal, there's character here, little zero guy. Right, there we go. So this is basically like if you better to sleep because fixing would be better when you're not sleeping. Right, that is true. Yeah, I was thinking that as well. So what this means is arguments. That zero just means nothing, really. So if you type in rename into the terminal, but nothing else, like you don't put any, you know, like arguments in there. So that's what I mean by if no arguments, and you know, whatever. That's what I meant by that. Like if no arguments, like arguments would be like, rename this to this. If you didn't put like this to this and you just did rename without putting anything else, then it would go, it wouldn't error out, it wouldn't give you an error. Terminal write string. It would write a string, telling you how to use it. Usage, that's how I spell usage, right? Oh wait, no. I had it right the first time, yeah. Rename, old name, new name. Now return, which is just put it back here. Now we go split into two file names. Const pointer to second equals arguments, and fi equals 0 char old name with the array of fi, so 0. Wait, hang on, no, 13, yeah, because up here you've got the other ones that are 13, yeah, see, file name, like 13, it's like 13 characters, or 13 all names, I guess you can say. 13 while the second and second does not equal empty character and less than 12, so while second and second does not equal blank character and fi is less than 12, old name with the array of fi go plus plus, which equals pointer second plus plus. Old name array of fi equals, wait, no, hang on, yeah, 0. If second equals what is it, blank character, yeah, blank, yeah, equals blank, yeah, if, then this will be second plus plus, wouldn't it? Second, no, not space there, just second plus plus. Now if fat32 underscore rename underscore file, we got old name second equals 0, which is 0 is a good thing here. Terminal underscore underscore write string renamed to, now we'll leave a space there, but we won't do /n, like /newline, because that's actually something I've got to do here. That's actually bad, because you want to do this, but right here I don't want to, because I don't want a new line right now, because I still want terminal underscore write string, and this will be this will be second, as in like second name, and I want that to be on the exact same line as everything else, so that's why I haven't put new line there, but now I do need a new line. So, but the thing is, rename to, that's all I need, so I can't do another terminal write string to just do /n, so I need putchar, which puts down one character, and even though that may look like 2, the / and the n, it is seen as 1. And now we go else, in case it didn't equal 0, which would be bad. Terminal underscore write string. Write string rename file not found /n, and also boom, which I forgot to do here and here. That would have been bad. Okay. Bam. And so now I need to hook this into shell execute, which is down here. Else if shell underscore s so now we go input. This is where user input actually is. So if you do input rename, which is 6, and now what this 6 means is, you see how rename RENAME, and then RM write WRITE, boom. That's pretty much, so it tells it how many characters to look out for, really, I guess you can say. I'm not 100% sure, but yeah. So now if rename is entered, it will run cmd underscore rename, and it will have to get arguments, get underscore args, get its arguments, say for like input, which is 6. Boom. And so now we go up to cmd help, which will be in here, as you can see, right, because that is about. Now this is the help page. So we have write, and now I feel like after write we should have move, right? Okay, so help clear echo ls list files and directory cat print file contents. Right, yeah, it should be terminal underscore write, and then there's a plus underscore write string 6 7. The fuck you mean 6 7? Where does it say that? And so now we go rename. Oh, it's not a move command. I'm not getting a fucking move command. yet anyway. What the fuck I mean move command? I was literally just been working on a rename command the entire fucking time. It's like, oh, what about the move command? Oh, shut up. I'm actually getting so tired right now. I think rename a file /n, wrong /n. And so now, okay, that's actually CLUSTER. Okay, this is actually not the worst right here. Okay, so what I will do, print screen. I'll take a screenshot of that. I'll go files, pictures, screenshot. Okay. I will fix these. Wait, hang on. Yeah, again, sectors per cluster, and then re-earn. Those are the only real issues. Well, for this piece, because I could also fix them up, and the next thing you know, this, and nano-l fat32.c. So then it's in line 611. So this 611 cluster, and then 615 cluster, and 641 where does it say? Oh, that's just an error, so 683 now. Not an error, a warning. Re-earn, so return. There we go. And now, is that it for? Yeah, okay. So X, Y. Wait, no. Control X, Y, enter. Now, CD ls make clean. Now, make again. And I was cleared. Yeah, okay, so I think it's done it. I did it. Okay. It works. These are just warnings. Doesn't matter. Right? It doesn't matter. Let's reformat the disk. There we go. Reformatted the disk. And now let's run. Let's run it. Gonna open GordOS.iso. Wait. Oh yeah, make ISO. There we go. There we go. Okay, guys. Let's test this. Help. Now we have rename. So we go ls. We still get the debug stuff. Hopefully this works. So we'll touch test.txt. Now we go ls. Now we have test.txt. Now we go rename. It's input file to output file, wasn't it? Yeah. We'll just type in rename. Yeah. Old name, new name. So rename test.txt to let's go but stuff.txt. Let us quit, I guess, and reopen it. ls, still test.txt, okay. So it hasn't really worked. There are some issues. Maybe I should actually have a look at these warnings. But as of right now, I think I'm happy with this. While technically it doesn't work, it works. Not really, but you know, it does do kind of what it's meant to do. So, you know, can't really, yeah. Anyway, I think that will be it for today. It technically didn't work, but in my head I call it a win because, well, I didn't get that many errors when making it. I think I got warnings, yeah. I mean, NI might be uninitialized. Yeah, but I got warnings. I got some errors, but the errors were just like basic spelling mistakes, so I'm happy with this. I mean, it technically didn't work, but I'll just do it again tomorrow. I mean, yeah, I guess tomorrow. Hope you guys enjoyed. Probably was a bit confusing for a lot of people. Yeah, hell, it was even confusing for me at points. So, you know, let's just name this document. I'm just saving my document as init setup. There we go. There we go. Okay. It's